Welcome everyone, and thank you for coming to this afternoon session. My name is Charles Bedu from the Energy and Environment Research Group, University of Swansea in Wales, UK. My talk today looks at tidal stream turbine arrays in a demo site using a generalized actuator desk CFD model. The outline of my talk consists of a brief overview of the GAD-CFD tool, which was developed at Swansea, and an example case we are working on, including some interim results and our future plans. We have developed a new generalized actuator desk CFD model, GAD-CFD for short, that achieves the required accuracy for simulating horizontal axis tidal turbines and their wakes. This new method combines a finite volume CFD code with additional source term representing the rotors, including correct consideration of losses along the foil by modification of the distribution of downwash, recognition that foil cross-section varies along the length, dynamically changing Reynolds numbers, and the application of a tip loss radius correction. Also reported are foil lift and drag coefficients and their variation with thickness, surface roughness, and Reynolds number, which is necessary for the proper characterization of the whole rotor. The model has been compared to several lab-scaled experiments with good results achieved, and our aim is to improve the GAD model capability by developing and incorporating more realistic bathymetry characterizations, which is expected to be an important factor in real-world turbine array operation, and to provide an open access, clearly documented tool for the marine industry and research community to help in their individual device design as well as array layout optimization for energy output maximization. The tool is active now for anyone to use, so if you're interested, you can drop us a message and we'll be happy to assist you with how you can download and use it, as well as provide support. The input details for the tool are: for the rotor, you have to input your twist cord, lift and drag, TSL, or control whether you want to analyze tug or pitch regulated tidal stream turbines. You can include your support structure and details about your tank dimensions or the bathymetry, so velocity, turbulence details, and the geometry of the bathymetry itself. The output of the tool includes CP, so power details, thrust and torque, local TSL, and weight details. More details about the tool and the mathematics involved, including benchmark test cases, can be found in the following references. We are working along with some of our partners using our model to investigate the feasibility of a tidal energy demo project at the Bay of Fundy region situated in eastern Canada. The bathymetry of the region is shown on the top image. The boundaries of the area of interest is shown in the blue image. The image below is a zoom in of this area, which occupies a part of the site where a number of notable bathymetric features present potential engineering challenges regarding the design of tidal turbines. The presence of such extreme features is likely to result in a number of complex flow phenomena. We first and foremost validate our model using ADCP measurements at a known bet A location shown as A1 in the bottom image, and then characterize the flow in the vicinity of the region of interest. After which we investigate the performance of 6 tidal arrays labeled T1 to T6 bottom image within the region of interest. The turbine used here are fixed pitch variable speed rotors with optimal TSR of 3.0 based on the average inflow velocity. The turbines have a diameter of 10 meters, which is a reasonable representation of the scales of turbines likely to be deployed in these environments. The turbines are consistent throughout the analysis, and the tower and nacelles were neglected in all cases. An explicit grid layout is required for use with the GAD-CFD technique Thus, a blade box must be defined. The blade box represents a rotor of 10 meters in diameter with length of the box in the flow-wise direction fixed at 0.1 d. The chord length and twist angle characteristics of the blade are presented on the right image. These profiles are used to determine the occupation of the blades over the blade box region to determine the exact location of the blade forces. The CFD simulation used a Reynolds average Navier-Stokes type simulation with K epsilon arranging turbulence model. Computations were carried out for an ebb scenario, inlets in red and outlets in yellow, with spatially varying velocity field at the inlets of the domain. So you see bottom image. Roughness of 1 meter is applied to smooth the bathymetry throughout the domain at the sea floor boundary. And for the run solver, we used an open source tool, OpenFOAM. So the grids. The domain had dimensions of 2350 meters east to west by 1700 meters north to south, and all grids were created using block mesh and SnappyX mesh in OpenFOAM version 6.0. Mesh resolution of 2 meter in the horizontal and 1 meter in the vertical directions with total element size of approximately 40 million was used, with additional 5 million dedicated to the rotors, and runtimes vary between 18 to 24 wall clock hours for the ebb scenario, including rotors, on 2x14 processes. So let's look at some of the results. So comparison of the velocity profile in blue for the CFD with ADCP measurements in black in bet A region shows that the lower part of the boundary is relatively close to the measurements. The differences between the curve was approximately 2%. There was no experimental ADCP data for the region of interest. However, profiles are shown for a virtual ADCP data in red, which shows a strong share near the seafloor and a more vertical velocity profile above. Mean horizontal magnitude at 55 meters below sea level is shown on the top image. The horizontal velocities are the magnitude of the U and V velocities with directions indicated by the overlaid whisker plots. The flow is from right to left. Plots are also compared to Wilcox et al., who carried out similar analysis using a detached dissimulation type analysis. Can be seen that the RANS computation compares well with the DES simulations, with slight differences resulting from the DES simulation using additional synthetic turbulence at the inlet, which wasn't used in the RANS computations. The mean velocities at 60 meters below sea level compares well with the DES simulations shown here. The results matches closely with each other. Next slide shows mean velocities at other 12 locations below sea level. Most importantly is the complex flow around the volcanic plateau. Approximate shape of the plateau is at 45 meter depth, where the results show a strong layer of complex flow near the plateau surface that covers it completely below a water depth of 25 to 30 meters. So runs with 6 rotors placed at the region of interest are still ongoing. However, we've included an initial results which we received prior to the session. The top is the left is the horizontal velocity taken at hub height for a rotorless run, and the hub height is 27.5 meters below sea level. The boundaries of the region of interest is also visible in this image, and the right image shows the visualization of the mean velocities at the region of interest, also taken at hub height. The flow direction is from right to left at TSR of 3.0, where we see the influence of the rotors on the flow are still visible further in the wake. This is very important, especially when choosing site to deploy further rotors. Results with the rotor runs will be made available when ready. Just to summarize, the GAD tool is efficient for simulating tidal stream turbine response to realistic inflow conditions. Model validation has been conducted with GAD-CFD measurements, and due to the computational efficiency, such an approach, especially compared to fully resolved turbine models, make the GAD-CFD suitable for modeling arrays consisting of large number of rotors, and for conducting multiple model runs under varying tidal and machine operating point conditions. The model sits between highly detailed blade resolve models and larger ocean models and atmospheric models. The next step will be to complete and validate the multi-device run and validate the target vert location, as we've just received some measurements at this location, and then explore the impact of variable inflow conditions on varying configurations of multiple devices. We'd like to acknowledge DP Energy, our partners, for providing data used for this work. The work was also supported by the CELCI project funded by the European Regional Development Fund through the Ireland Wales Cooperation Program. Thank you very much for listening. I will be glad to take any questions.